So good morning. It's great to be here. I see a lot of familiar faces that have stuck around for some presentations I've given around the state or here at CTC last year. The irony is not going to, falling unnoticed that I'm going to talk about warmer winters, given that we woke up to single digits on March 6th this morning. So I certainly understand that irony. But there was a lot of good stuff in Dr. Davis's previous presentation, and he mentioned changing climate, and that's what I want to get to. And I want to use 2018 as an example. So hopefully you all have fond memories of 2018, and they're fresh on your mind, and we'll talk about those things. As a primer to that, obviously the power of weather impacts us all, right? We're not immune to extreme weather here in Ohio. And each generation sort of has that marquee event that they always can remember, or important event in their life. If you think about Ohio's greatest weather disaster occurred in 1913. With the flood of 1913, where 6 to 11 inches of rainfall fell across much of the state. And certainly that was a very impactful event. This was my hometown of Miamisburg. And certainly the flood of 1913 brought along the levee system there, the conservation districts and things that were happening along the Great Miami River out southwest part of the state here. I missed the blizzard of 78 by a year. I certainly would have liked to experience that, despite what most people tell me. I certainly want to be buried in snow sometime in my life. I may have to go up to Ashtabula County or something like that to experience that. And of course, in 2012, we had the derecho. Strong winds, right? Big, powerful line of thunderstorms that came through, moved very rapidly. We had a lot of 80 to 100 mile an hour wind gusts throughout much of the state here, and certainly it did a lot of damage. So the power of weather, weather impacts us all, and as farmers we know that, right? We're living this day to day, and farmers are generally resilient to a lot of the impacts that happen anyway. If we look at our extreme weather, it is very costly, okay? This is from the NOAA looking at billion-dollar disasters, and this is specifically for Ohio. Between 2008 and 2017, the costs of natural disasters in Ohio. And if you look at the top two, both flash flooding and also long-term river flooding, that's over $200 million in damages between 2008 and 2017. So flooding, rainfall, that's our high-impact event. That's what we see. And if we look and we think about the face of our changing climate, it's certainly about water. It's centered around water. We're seeing more and more water, and a lot of that damage is coming because of that. I think there's a limit here. All right, so if we think about weather, and we get up every morning, if you think about a typical day, we might say in the summertime start out around 60. By afternoon, we're 87, 88 degrees. At night, we're back down around 60, 62. So big temperature swings every day, right? 20, 25 degrees every single day. If you could play the top left video, Greg. All of those fast and rapid changes that we think of in terms of weather, the rapid changes in temperature and winds and all of that stuff, they happen on such a fast time scale that it's hard to depict patterns. But as meteorologists, what we do is we draw back and we look at the larger scale. And once you start looking at these things, so this is a series of satellite images for the surface of the Earth for an arbitrary month here. Once you start thinking about all those rapid changes that are taking place in this picture that we see, you start to develop patterns, right? And you see these fast-moving storms across the Southern Ocean. Across our region, we have these storms as well, but they stretch out north to south, okay? Or maybe you see these pulses of thunderstorm clouds along the equator. These long-term weather patterns are essentially what we think of climate. They dictate what our overall climate is for a longer period of time. So if we escape out of this, yeah, that should work. And if I were to ask, some of you have seen this already, but if I ask you what this picture is, it's kind of hard to see because we're really zoomed in. But if you go ahead and play this, Greg, in a second, you're going to see a pattern develop over time. You may already see it, right? You see this. Is that a paw? I think that's a paw. Yep, that's a dog, right? And the dog is walking along with the dog walker. Now, that dog is driven by some natural tendencies, right? It's hungry. It sees a McDonald's wrapper with leftover burger. Nope, I need to use the fire hydrant here. Maybe there's another good-looking dog down in this direction that drives that dog in that direction. Now, it may be going opposite direction at any one time to the dog walker, But we expect them both to be here in just a couple of minutes. And what's that? That's based on the path that this dog walker is taking. Okay? Now that dog walker could move in this direction, say if a car came along or some big push to push it that way, but it's not likely. We have confidence that the dog walker is moving in this direction, even though the dog is meandering back and forth. That's the relationship between weather and climate, where the dog is the weather, the dog walker is the climate. They're not always moving in exactly the same direction, but in the general direction, because the path of the dog walker is describing that path. So that's a way you can think about weather and climate. Okay, I'm good on the videos. Now, if we look at what our temperature has done, we take all of our modern technology, certainly since the late 70s, but our weather instruments that we've had since the late 1880s, and we look at how temperatures have changed across the surface of the Earth compared to, say, a long-term mean. What was the average for the 20th century? You can see from the late 1800s on, you get these regional areas of warmer and cooler temperatures. But over time, we see a tone change, right? So once we get past 1970s, we see a strong warming across the Arctic and much of the Earth, and also the Antarctic. So the Arctic regions are warming faster, but certainly things are warming here. Now in Ohio, most of the U.S., the 1930s was a very warm decade, our warmest decade. If you look at our record during the summer, 34, 37, that was regionally when we saw most of our record summertime highs. Okay? So there's a lot of details in this, and those are the details that I want to get into today. I think we'll go ahead and skip that one. All right? So I'm going to do that by putting last year's season into context. Right? Last year's growing season. And I defined it here from May of November for 2018. And you're going to see a lot of maps here where we've basically just centered in on Ohio. And we're looking this one. This is the May through November departure from normal, departure from a long-term mean, which we consider 1981 to 2010. You see a lot of orange on that map. So most of the state, we were between 1 and 4 degrees above average for that entire time. So climatologically speaking, if we look at last growing season, it was warmer than average. Okay? If we look at our accumulated precipitation across Ohio, just for these months, from May to November, most of us picked up between 20 and along the southern part, 40 inches of rain just between May through November. Okay? We had sites for the entire season, for instance, down here near Cincinnati, of over 75 inches of rainfall. We had our record wettest year in Columbus of over 55 inches of rainfall. So that's kind of gives you a perspective around the state. And if you look at how it's compared to average, almost the entire state is above average, at least a couple of inches above average, and last year as much as 15 or 20 inches above normal in terms of our rainfall last season. So that's kind of 2018 snapshot. And what I want to do is go through a couple of the things that we're seeing and tie them into the long-term trends that we've also seen. I asked the question, who ordered the water? So this is an evolution of our soil moisture last year based on what we saw. So we had a very wet February, dry out a little bit, especially across the northern part of the state during the summer. And then once we got into fall, certainly we had a very wet fall. Right? That was generally how we characterize the entire season. And these greens just represent well above average in terms of the amount of soil moisture that we have, and we have out there right now, either locked in the frozen soil or frozen or sitting on top of our fields. Now we can define our growing season length, and I've done it a couple different ways in this map. And if you happen to pick up the E-fields or heard the talk about E-fields yesterday with Elizabeth Hawkins, this figure is in there as well. But if we look at our last frost date to our last frost date to our first frost date, defined as 32 degrees, that's that map down here. So generally about 170, 175 days last year. If we use 28 degrees or a hard freeze, right, you get a lot longer season if you're across the southern portion of the state, or influence of some of the municipalities, right? Toledo influence, Cleveland influence, and then parts across the southern portion of the state. Now our season length last year was 10 days longer than the long-term median, right? That long-term average of our growing season length was 10 days longer, and that matches what we've seen across much of the Midwest since the early part of the 20th century, 9 to 10 days longer of frost-free conditions, okay? But let's jump into some of the details because they're really important, and I would define 2018, as much as you probably would as well, as a year of extreme variability, right? Month-to-month variability was pretty stark. So if we think back to last winter, we had a fairly cold January, okay? We didn't get as cold as we did for a couple of days this January, right? But we certainly had a cold January overall and a very warm February. So last February was a series of Februaries where we've seen temperatures close to 80 degrees, right, for several locations. Much of the state last year where we got up close to between 70 and 80 degrees. So very warm in February, and it was also our second wettest February last year. Okay, we had the highest crest on the Ohio River since 1997. So it was wet, and that sort of, when you think about wet soils, it takes a while to warm up, right, in the springtime. And if we look at our spring last year, and we look at it from two perspectives, one from a weather perspective, it was the 9th coldest April on record for Ohio, going back to 1895. So our temperatures last year were about 5 to as much as 9 degrees below average for April. Okay, when everybody's just really eager to get out there and get working. And then what happened in May? We flipped the switch, and we had our warmest May on record since 1895. Now, climatologically, what does this mean? Well, we add April and May, we divide by 2, and we had an average spring. Did we have an average spring? Did we have a normal spring? No. Extreme month-to-month variability, right? We had a lot of temperatures in May, some 5 to 10 or even 11 degrees above average for May. So we had some rapid growing degree days last year, right? Accumulation of growing degree days. This is a tool from U2U here. The purple line showing the average growing degree day accumulation throughout the year. The green showing 2018. And around the state and up in this region, once we got to about late May, those growing degree days were really accelerating, especially during June. We had some rapid acceleration of growing degree days into the June timeframe. And why was that? Well, if we look at the temperatures last summer, these are the average temperature departures from June through August here. Much of the state above average. And these were the overnight lows. And you can see a lot of our warmth last year was driven by overnight lows. June was the 4th warmest June on record. A lot of that driven by overnight lows where we're staying 70, 75, 77 degrees at night, right? That's when we get the accumulation of those growing degree days. So what does the long-term trend look like? I want to pause here for a minute to take a look at this. We've seen warming across the entire U.S., and in Ohio it's between 1.5 and 3 degrees, much more downwind of Lake Erie here. Okay? And most people ask, okay, 2 to 3 degrees, that's nothing. You just said we go up and down 25 degrees, and that's the difference between weather and climate. That long-term perspective versus the weather perspective. But there's a lot of details here. It's driven by wintertime warming, warmer winters, and during the summertime, it's not driven by our daytime highs. What's happening during the daytime? Well, if we look at our coldest temperatures of the year, that minimum temperature we fall in the winter, we've warmed 2 to 4 degrees over what we saw in the early part of the 20th century. Our winters are 2 to 4 degrees warmer, that minimum temperature, absolute coldest temperature we reach. And that's true for much of the country. But if we look at our summertime here, and you see much of the Midwest and Ohio Valley with blue dots representing cooler summer daytime highs, those maximum temperatures we reach. We don't see the 98, 99, 100, 102 as often. Okay? So our daytime highs during the summer have cooled. Is that surprising? It's a little surprising. Our daytime highs have cooled, our winters have warmed. But our summer warming is driven by overnight lows. So this is a suite of a few cities last year. These are record overnight lows, so high record overnight lows, right? 11, 12 throughout the growing season here. So we just had exceptional warmth during the nighttime, and that fits what we've seen in a long-term trend, right, since the early part of the 20th century. So the temperature impacts, and this is being tied into conservation and things we're thinking about here. The previous speaker talked about, new or expanding harmful algal bloom species and things like that. Those are tied to the temperature impacts. We can also think about stress on humans and livestock, increased weed pressure, insect pressure. All of these come along with those extended growing seasons, warmer winters. Things are more hardy. We're shifting our hardiness zone, for instance. So jumping back into last year, and we look at last summer, again, plenty of rainfall throughout much of the state for summer, but we did dry out a little bit across north central region, and we dried out quite a bit across the northwest as well. As a matter of fact, if we look at our extent of summer dryness last year, and this is the U.S. Drought Monitor, we had official drought across Wood, Ottawa, Seneca counties, parts of Lucas County as well, in a moderate drought category. Okay, and if you're the southern part of the state certainly didn't see any of that type of summer dryness. So I think most folks were heading into the fall thinking about harvest, and things were pretty good. If we look at September and October, exceptional warmth in September and October, again, highly driven by the overnight lows. And then what happened in November? We flipped the switch again. We had our 10th wettest and 4th coldest November on record, and unfortunately it left crops in the fields and harvest really behind schedule here. So this was the back and forth. As far as the rainfall, 3rd wettest autumn on record going back to 1895, 2nd wettest September on record, highly driven by tropical activity. Right? So we had the remnants of Tropical Storm Gordon, dropped 8 to 10 inches of rainfall down across the southwest portion of the state, less here across the northwest, and Hurricane Florence kind of largely missed the northwest part of Ohio. So how does that fit into the precipitation trends? And this is the big one, I would say, the big issue that's in the room and the face of what's happening here in Ohio. If we look at our precipitation trends, both annually and seasonally for the U.S., precipitation across the country has gone up 4% since the early part of the 20th century. For Ohio, it's 5 to 10%. Okay, we've seen an increase of 5 to 15% across Ohio, the increase in the amount of annual precipitation we're seeing. And that's largely driven by our fall trends. We see more fall precip, okay, 1.5 inches more every fall now than we did in the early part of the 20th century. It's also the character, the intensity of the rainfall events, right? That additional rainfall, that 10%, 15%, isn't evenly distributed across the entire season or across the entire year. So we can break this down a lot of ways, and I do this kind of just to show that we're awash in statistics explaining the change in our water situation, right? If we think about our heaviest 1 in 20 year event in the fall, for instance, that heaviest event has increased about 1/4 of an inch. So instead of 1.5 inches, it's now 1 3/4 of an event, right? We think about our 2-day precipitation events exceeding that typical once every 5-year interval. Big increases in the number of 2-day events that exceed that threshold, right? We're talking about our 4 to 6 inch rainfall over a period of 2 days. Big increases in our 2-day events. We hear a lot about our 1 in 100 year events or 1 in 500 year events. We can standardize that across the country, and the Midwest has seen about a 42% increase since the mid-20th century in those 1 in 100 year events, those flooding events that we see. Okay? So what does that look specifically like? What does it look for Ohio? Ohio sees about 39 inches of rainfall if you average the entire state. Most of it falls across the southern portion of the state, less around Toledo, and northeast has a bump up because of lake effect, right? But generally it's 39 inches, and if you look throughout history back to 1895, you can see since about the mid-1990s we've had almost a stepwise change, almost a new normal here of about 41 inches of rainfall for the state. Along with that, we've seen an increase, a stepwise change in our extreme precipitation events, those events greater than 2 inches. And there's only 3 other peaks in our history that really challenge what we've had persistently for the last 20 to 25 years. And that's 1913, 37, and 59. Okay? These were all major flood years in Ohio. So the point of this graph, right, flooding is much more than just a precipitation story. It's a human story. How do we steward our natural resources? How do we steward the water? What do we do with it? How do we store it? Right? This is a persistent flood threat, a persistent threat from extreme precipitation. That's what we're seeing. Okay? So we've already talked about harmful algal blooms with the previous speaker. Obviously, these changes in the precipitation event are part of that complex story as well. Right? through erosion and other runoff mechanisms here in terms of the amount and quantity of water. So we see a lot of events, 5.5 inches of rain in 2 hours, 4 inches of rain in 2 hours that flood interstates. We are seeing a much more of these type of events occurring. If we just focus on the Lake Erie Basin, and it extends both west and east here, but if we just look at 1950 to 2014 and how the character of rainfall has changed, we can break this down a couple ways. I'm just going to fast forward and just look at, since 1950 through 2014 here, and we're looking at events greater than 1.5 inches. They're been, according to 1.5 inches, 2 inches, 2.5, and 3. But we see this pretty stark increase here in the number of events that we're seeing. Over 16 events on average that we see more than 1.5 inches. Okay? This is the change in that character of the precipitation where we're getting higher frequency rainfall here. All right, so what are the risks? What are we thinking about? And it expands from rural to urban gradient in terms of the things that we're at risk for. But changing floodplains and water infrastructure health and increased transportation. Here I think we're really focused on, that intensity means potential for more runoff and contamination, right? Those non-point source. So we need to think about, and I think thinking about these from a conservation standpoint is really important. One thing we can do, and if you've seen and heard Glenn talk about, manure applications and opening up different windows, if we look just at our field work days that are reported on a state level, and we look at both April, which is the blue curve, and orange, which is October, and we go back since 1995 when they were reported, we have a year-over-year trend of about 0.2 days per year decrease in our suitable work days, right? That's 5 days that we've lost in April and 5 days of suitable field work days that we've lost in October, right? So we're squeezing the time to get things done in those months, or looking for alternative windows, for instance, if you think about manure application in the fall. Right? So that's 10 days. So that longer growing season we've lost because of precipitation and ties to suitable work conditions in the field. So where are we heading? We're just looking out to the mid-21st century here, and we're looking at our temperatures across Ohio. Average temperatures of 4 to 5 degrees warmer than what we think of our contemporary climate. Most of that driven by wintertime, and most of that driven by overnight lows. Okay? And then if we look at our projected change in precip, like the previous presenter showed, increases on the order of 3 to 4 inches more precipitation per year over what we see right now. Okay? So why did I use 2018? Well, we've been dealing with a lot of water for a while here. So I asked the question, what if I told you 2018 is our new normal? Who's raising their hand? They want 2018 year after year, right? That's not realistic, right? We know that 2018 every year is not going to be exactly like 2018. But if we look at the boxes that 2018 is checked off, from a longer growing season, warmer temperatures during the winter and at night, higher humidity where we had record humidities this fall in October, more rainfall overall, more intense events, more autumn precipitation. That checks all those boxes, okay? That's what we've seen. Those are the observed trends that we've seen. So we've got a lot of water that's here to stay more often than not. Right? So we could think about a 2003 Ohio climate, and where will we be in the future? Let's just go to 2030, where we're looking at a Virginia winter and a southern Illinois summer, okay, in terms of climate. If we're going out to 2095, when we're thinking about our children and our grandchildren, we're talking about a Carolina winter and an Arkansas or a West Texas climate during the summer. That's what we're seeing, where 50 or 55 inches becomes more the norm, right, than the exception. So in terms of thinking about conservation, I'm here to stir conversation among the community, right? Because I'm not a conservation professional, I'm not a soil scientist, but I think climate and the changes that we've seen here locally can impact our decisions. So how robust are our practices to increased intensity of rainfall, of residence time of the water and the nutrients, right? Things about adequate cover, are those practical? Reduced runoff, promote infiltration, all these things, right, are tied to we're seeing more water, and we're likely to see more water into the future. So it's very important to understand how our local climate is changing so that we can build resilience to this, right? Because it's not going away. We talk about climate change as a threat multiplier. It makes what we do harder, right? So we have to be really, really, I think, constructive and creative about how we manage our natural resources from a water standpoint, from a crop standpoint, and from a, just overall natural resource point of view. So with that, I want to thank you, and we've got a couple minutes for questions for sure, so thanks. Yeah.
I know, Aaron, I heard you speak before. You brought up basically some of the change kind of occurring due to water, and was that semi-related to, let's say, center pivot out west? And then, I guess, does that ring a bell, or is that my way off base on what you said before?
I don't recall ever talking about center pivot and irrigation and things, but do you know when it was? In terms of what's happening, going to hear here.
Like some greenhouse gases being held in basically by water.
Yeah. That goes back to the intensity in the agriculture that we've seen across the Midwest, right? If you think about those summer daytime highs and why they are cooler, this is what I was talking about then. Dry air. If you think about 1930s. When we had a lot of the spring deficits in rainfall, and you think about dry air, it heats up really rapidly. And so you can get those temperatures that climb quite a lot. So what the research is showing is that agricultural intensification in general, or we can say like the 20th century corn boom, or the Midwest region that now is just, that breadbasket, right, of agriculture for the world. You've got crops sitting there, and more crops and intense agriculture, and so you get strong evaporation, you get more water vapor in the air that does two things. It keeps your temperatures from getting as warm during the day, but it keeps your temperatures at night warmer than they otherwise would be. And as fronts come along, if you've got more actual water vapor in the atmosphere, okay, those fronts wring that precipitation out, and so we get these heavier, intense rain events. And so that's the tie between agriculture across the Midwest making a direct change on the local climatology of the Midwest, right? And then that's where irrigation comes in and more water and that sort of thing. No, it's okay. Yes, sir.
This is a question just to try to understand the temperature data a little better. You probably have used many sources of your temperature data, and minimums and highs. Is within all that data, is there any weighting of temperature during each day? For example, like taking a temperature each hour or something like that, or is it primarily based on minimums, highs, and lows?
Yeah, absolutely. And there's actually some good recent research looking at the different. Yeah, so the question was, when you look at the temperature data, is it based on your high, your daily max high, your daily minimum, and you divide by 2 to get an average? Yes, that's how it was designed to do in terms of a long-term average. There are a lot of observations that are taken hourly, 10-minute, 5-minute, 1-minute averages, and you can look at those averages, and statistically there's no statistical difference. But there are small differences there. But generally, the National Weather Service, because of the way the observations were set up, a lot of this was based on volunteer, right, co-ops, co-op volunteers that were taking these measurements, so not to be too kind of, having somebody have to take a manual observation every hour. That's how it was initially set up. But like you said, we have vast data sources, different sources that we can corroborate among the data to show those consistent and persistent trends among the data. Yeah.
We're going to have to thank Aaron.
I'll be around today, so.
Thank you, Aaron.